Yes, it's
Science time. It's science time. We're going to talk about fields. So write down fields. Science time. It's time to talk about fields. The first thing that your book mentions on, well, let's rewind a little bit. We just, not on the video, but we just talked about what kind of forces in general.
Gravitational.
Yeah, non-contact specifically, they were gravitational, magnetism, electricity, right? Forces that they can work how? How are they different from what we might think about as forces usually?
They don't have to touch.
Right, they don't have to be touching. So let's write that down first. We have, in case you forgot to write it down or in case you didn't, non-contact forces. Let's think of a good scientific definition for non-contact forces. Yeah, that's an example, but let's think of a definition.
forces that don't have to touch an object.
Okay, what do you think is the matter with that exact definition? What's the problem with saying forces that don't have to touch? You're right. Like that's conceptually correct.
Because forces is in
Yeah, because forces is in the word. So let's try to use it without saying the word forces in the definition. But everything else you said is right. So you said forces that don't have to touch in order to work. But what else can we say?
objects that don't have to touch.
Are they objects though? All the time? I wouldn't call electricity
Material that doesn't.
But it's not material because that implies that it's matter. They're not matter. So they are. What's the definition of a force? Maybe we just use that instead. What do forces cause? They cause a
reaction. Motion.
Yeah, so a push or a pull, right? A push or a pull. So let's call it that. Push or pull. Push or pull on, we will use an object because that's what they act on. Push or pull an object that is not touching the object. We can say, I'm going to put this in parentheses, they act how? Act at a, non-contact forces act at a what from the object?
What? Distance?
Distance. Act at a distance. Yeah, they don't have to be touching the object. And some examples of this, well, your book provides this. Well, your book provides this maybe example. It says, is a stink field, is how it starts, is a stink field a real field?
Yes.
Well, let's think. What do we do when we have a question like this? We have a claim, evidence, reason, right? So what's your claim? It doesn't have to be right, but just raise your hand. What do you think, Cyrus?
Yes.
Is a stink field a real field? Yes, Cyrus. What's your evidence for that?
Not a clue.
Okay, so you have to have evidence for your claim. What do you think?
The further away from a smell, the less you can smell.
Okay, good, because we know about the non-contact forces we're already aware of. Gravity, magnetism, electricity, right? The further away we get, the smaller those things get. And it's true for a stink field too, right? So some evidence is that, like these non-contact forces that are real potentially, the stink field gets weaker the further away we get. What do you think, Peyton?
Yes, I believe, because if you walk into a room, you can smell it, but then when you step right back out, it's gone.
Right, you're not actually touching. You don't have to be nose down in dog crap to know that there's dog crap around, right? Like you don't have to be touching it to know. Okay, so there's two pieces of evidence.
I mean,
And what's the reasoning? What's the reasoning behind it? Like how?
The order,
What's that?
the smell of it, how it lingers.
Yeah, so it stays in the same area maybe, right? So there we have a claim, yes, it's a real field. Some evidence is that we don't have to be touching it, mercifully. And what was the other one? That it gets weaker. That it gets weaker the further away we get. It says, here's the question: on a hot day, the garbage stink. That's
A garbage.
yeah, that's a kind of good name for a band. A garbage stink. Don't name your child garbage stink though. On a hot day, the garbage stink covers a, what do you think, area than on a cool day?
larger.
Probably larger, right? So there are different varieties of stink. I would rather sit near the garbage can when it's full of
Garbage.
what?
Stale bread.
Nothing.
Stale bread.
Probably stale bread. The smell from the garbage can is
Stronger.
well, aggressive.
Weaker.
The smell of the garbage can is weaker when I sit further from the garbage. Adding more garbage to the can makes the smell
Stronger.
okay. People passing the garbage can are usually affected by the smell coming from the garbage can. Yeah, so I mean, really, we have a garbage can in here, and I don't feel like I'm affected by them.
No,
ever.
it doesn't smell at all.
Yeah,
Because they don't put that much.
Well,
just,
that's because
like,
you don't put food in it.
you put like
I do.
paper in.
Yeah,
I
these
threw it
are. In fact, usually you might even hear me call them that. I call these things waste baskets, like we short for waste paper baskets. So that's really always.
Our neighbors put like a bunch of stuff inside the dumpster that's behind our house.
So
Yeah.
whenever we go to throw trash out, it smells like a dead opossum.
So,
I
this kind of makes people laugh when I start the story, but I tell this story a lot. I say, I've never been to New York City, but I have been to Rapid City, and then people laugh at that. So, okay, but that's not, and I say, that's not the funny part. I have been to Rapid City, and so one time I was in Rapid City, it was July, it was probably like 100 degrees, and we got out of my car in the parking garage. I don't know if you've ever been to Rapid City, but there's that parking garage downtown. We parked in that, I got out of it, and I said, that reeks. Like there was a dumpster right there, and it smelled so bad. And then my wife said, this is exactly what New York City smelled like, because she's been to New York City. And so that's why I say, I've never been to New York City, but I've been near enough a garbage can. And she said, that's what, like in New York City, there's so many people in such a small space that when the garbage pickup takes place on the street, like people just put their garbage on the street, and the garbage man comes along and collects it. But in the meantime, the garbage is just sitting there. So when you walk down the street, especially if it's hot, stink field. Anyway, so is a stink field a real field? Well, we'll get to that later, but for one thing, we know that non-contact forces act at a distance. And we call the area, well, let me let you define it. We're talking about fields. What are some definitions of field? When I say field normally, if I were just to say field on a normal day, you would think,
like football field.
yeah, like a large area of
Rocky
hay or grass for
Rocks.
or rocks. It doesn't matter, but a field is, we know it has something to do with what? In all the cases that we use the word field, it has to do with a what?
Area.
An area. So a field, in science though, a scientific field, what we're going to call a, we could call it what kind of field? If we're talking about gravity and electromagnetism, we could even call it a force field, which, from like Star Trek or something, but a field of forces, right, is an area of effect of a, specifically what kind of force? What do you think? Non-contact force. A non-contact force. So the field we call the area around that force affects. And usually it is around. So look with me on page, there's a picture of a spider on 132, missed that, but on page 133 there's this picture. I'm going to recreate on the board for someone who doesn't have their book at home. We got a little leaf.
It's in a dog.
Shh. We got a little leaf, and I'm going to draw a really good version of a dog.
Yes. Beautiful dog.
Shoot it.
Hey, Cyrus, not appropriate. Okay, so this is kind of what the picture is, right? And if we were doing this 2 months ago, and I said diagram the forces acting on these things, we would draw what for the leaf? Yeah, the force of gravity acting down. There's probably not, because it's not saying something, but there is the force of air resistance. But we're just going to focus on gravity because that's one of our non-contact forces. Is the gravity acting on the dog?
Yeah.
Sure. But the thing that this diagram is showing you is that while before we just showed the force of gravity acting on the leaf and the force of gravity acting on the dog, the force of gravity, look in the second image, the force of gravity is actually what we call pervading. It's everywhere. The force of gravity is acting on every single thing in this entire picture, right? The air molecules, everything is pervaded by the force of gravity, right? The force of gravity is acting over all of this stuff at a distance. Yes?
Do forces act on like a dead thing?
Yeah, forces acting all the time.
Like even on like a dead animal, like.
Yeah, so the forces, but the leaf, we can think of the leaf as a dead object, right? But anyway, the force of gravity is pervading this, right? The force of gravity is all over the place. Even though we drew these force diagrams and we showed that the force of gravity is acting just on that thing, the force of gravity is acting on everything, right? It's everywhere. Even if you're in outer space, it's still acting. What? If we were 100,000 miles away from Earth, would the force of gravity still be acting on us?
No.
Yeah, technically. And if we think of the force of Earth's gravity as weak enough that it's not acting on us strongly, the force of gravity from the sun is still acting on us, right? The force of gravity is everywhere. It pervades the entire universe. What we sometimes call a field, right? It's acting over a huge area. In fact, gravity has a larger field than some of these other forces do because it acts at a longer range. It's weaker, but it acts at a longer range. Yes?
We're in one part of the world where there isn't gravity.
None.
Universe.
No, gravity is everywhere.
So like I couldn't go a billion miles away and...
Nope. Some
Billion
things,
miles planets.
good, that's a good question, Peyton, but some things gravity will always be acting on you in some way. Gravity is what we call a universal force. In
So
fact,
like
all
we
these
can't float aimlessly and not
you can
move.
float aimlessly, but because the forces acting on you are either balanced or the thing is so far away that it's not noticeably accelerating you. Now look with me on the next page. It says,
Like I can't
there's a diagram.
man.
There's a diagram of the sun, and it has all these gravitational field lines, these blue arrows, I'm on page 134 now, there's a picture of the sun in the same way, except instead of a dog and a leaf, the sun has these forces acting on it. Everything, technically everything in the universe, we talked about this before, technically everything in the universe is attracted to the sun's gravity, right? Some things it's attracted weaker than others because it's farther away, but technically everything in the universe is attracted to the gravity of my fingernail. It's just that most everything has some other attraction that's stronger than that, right? If I drop this marker, technically the force of my pencil here is attracting the marker as well, but we don't notice that because the force of gravity attracting it is much, much stronger. Do you see what I mean?
Yeah.
So everything, gravity is universal, which means that everything is always acting on it. So we have this picture of the sun here, and look, there's a picture of field lines acting on planet Earth and the moon. Look with me. I'm on this next picture here. It says, so we have a picture of the moon and the Earth and their gravitational fields. And it says, the lines around the Earth are closer together than the lines around the moon. This means that Earth's gravitational field is stronger than the moon's. Earth's stronger gravitational field keeps the moon in orbit. But look, if we look over at the moon, is there an area there where if we were near the moon's gravity would be affecting us stronger?
Yeah.
Yeah, because even though the moon has
Smaller.
a lower strength of gravity because it's a smaller object, if we're near enough, the moon's gravity would affect us more than the Earth's gravity. Does that make sense?
Yeah.
Okay.
You like shrink.
So, just like we talked about, gravity is acting in all these cases at a distance. Are the moon and the Earth touching? No.
Never.
Never. They're non-contact forces, right?
What
Acting
about
at a distance.
Cybertron?
Okay. Another kind of field we had already talked about. We talked about both of these already, but we have electric fields and magnetic fields, and so that's why I've got this little demonstration. I'm going to try to make sure you can see this on the camera. Get over here. Okay. Oh, I turned it on accident. Turn the lights off, please. Sedona and Leo, would you pull those blinds down so we can see this thing? I think this thing is so cool. This is a little... I have it plugged in over here by my microphone.
Shut it. 14.
All of them. Oh, Leo, you might have to get that one too.
We don't have money to stand with you.
I wonder how the camera is going to respond to this. Oh yeah, that's dark. That door needs shut. I can tell on camera.
Pull it down and then stop.
Perfect. Okay, now the camera shows up as completely black until I turn this thing on, hopefully. So this is a little glass ball. Listen, it's okay. It's fine, Cyrus. Sit down. This is a little glass ball, and inside the glass ball is a gas. And when I turn this on, all that's going to happen is this little coil in the middle is going to get charged, and it's going to
Light up.
ionize the air. There we go. Yeah.
Yeah, so like the one we had before with
Oh, I've seen those before.
So what's happening is the gas inside of there is becoming ionized, and the electrical field generated by this little pillar in the middle.
So is that a Tesla coil?
We get no. This is a different thing. This is called a plasma ball, or at least that's what I call it, is a plasma ball. But the gas inside of there is being ionized, which means it's turning into a plasma, and the glowing is happening because the air is made out of protons, neutrons, and electrons, right? Mm-hmm. And when the electrical current is passed through them, it rips the electrons off, and that ripping action causes them to glow. And that's kind of a facile definition, but it's more or less true. And so I've got this nice little... We can play with this later, but I just want to show you on the video. So we can tell it's acting at a distance because there's air in here, but my finger is not touching the little electrical pillar in the middle, is it? Mm-hmm. No, it's not touching it, but it's still... Obviously, when I touch it, it changes. And so it must be acting on it as a force. So the electrical force... It's a non-contact force. The electrical force acts as a field.
Well, technically, you're touching.
Like I said, we can. I'm touching the glass ball, but I'm not touching the little thing in the middle generating the electrical field. Turn the light on, please. Another. No, not the door. The light. Okay. Another thing I have here, and I hope you can see this on the camera as well. You remember when I spilled all the compasses out on the paper plate?
Yeah.
And there was a paper plate here. We had the magnet in the middle, and then all these little compasses around it.
Yeah,
they all pointed in different ways. Oh, these ones should be like this. Because basically the way a magnetic field works, or looks, is that we have a magnet like this, and the magnetic field lines kind of wrap around from one end to the other. Do you remember that?
Yeah.
I was gone that day, so
That's okay. But I'm going to show you again. So what's going to happen is, I have this little field plate here. This is a little container full of iron filings. I'm going to do another demonstration similar to this. But I have my magnet, my strong magnet, and you can see, can you see this at all on the board? Or on the... Okay. well, obviously they're attracted to it, but other way would be better. There we go. I think you can see that fairly well. It makes, so you can see the little magnetic field lines. You see how they're, trying to get it on the camera too, I'll show you guys in a second, but you see how it forms that special shape, kind of like the one I just drew on the board?
Yeah.
You
Like
see that?
parentheses.
Kind of, yeah.
Mom's
yeah.
doing.
So, hold on. And fields, you should write this down. Fields, these force fields, right? The non-contact force field have a three-dimensional shape. So I drew this on the board. Obviously the board is two-dimensional. I drew this on the board. Obviously the board is two-dimensional. But they have a three-dimensional shape. Kind of like this, but it's kind of like egg-shaped around it three-dimensionally. Colton was just telling us that he got a magnetic hourglass, right? And that forms a three-dimensional shape, like a little kind of spiky structure. And so what I'll show you is I have this test tube. I'm gonna put my fields have a three-dimensional shape. Oh heck, the test tube ain't big enough. That's really annoying.
Testy tubey.
Hold on. Okay, so now I have a correct size test tube. I'm gonna put my magnets in the test tube, and then I have this beaker of just water. I don't really want to do this on top of my book, but that's the situation I'm in. And then this is just a jar of iron filings. I'm going to put those in. Obviously the iron's going to sink, or most of it. Yeah, a nice little pile of iron there on the bottom of the beaker. See? Oops, over here would be better. And I'm going to put this in here.
Holy crap.
You see the three-dimensional shape that they form?
Yeah.
It's kind of hard. You can't. I mean, it's nice that it magnifies it, right? But it's kind of annoying because it's kind of hard to see. But you see the three-dimensional shape there? Mm-hmm. It looks almost like, I think, like a little flower, right? Like it's kind of like whoop, this shape and then that shape. And that's these field lines, right? That's the exact same shape I tried to draw here, but it's three-dimensional. So let me try to think of the best way to get this out of there without breaking everything. Okay, well, that didn't work.
Could you just tip it upside down?
No, because see the iron is also magnetically attracting the magnet. That's a good idea.
I was just wondering if the weight of it would.
No, the weight of it is not. Well, because
Like
the magnet has a
A
factor.
factor.
I'll deal with that later. But I also have brought out these little like scraps. It's the same demonstration that I showed you in the lab the other day. But if we get this balloon and charge it, how can we charge the balloon?
Rub it against your hair.
Yeah.
No, we can't rub your hair.
I'm gonna rub it against my hair to charge it, and then I have these little, just to show you that they do act at a distance, which you know, but gosh dang it, I have this little tissue paper here, and I'm gonna, look at that,
Hold up.
right? Because basically, the balloon has a charge, right? And even at a distance, the tissue paper is neutral, but the balloon has a negative charge, and so all the negative charges in the tissue paper have been pushed to where my fingers are, and so the inward facing the balloon is more positive, and so it
Is it
attracts
really,
it.
like, can you tell it's strong?
Do you see? I'm kind of trying to show you the
Yeah, it's
three-dimensional shape, though, where if I put it over here, it goes towards that one little dot, and so it forms that same kind of shape that I tried to draw on the board and that the magnets form. Field lines are generally shaped, right?
Jacob. Gotcha.
We got a Jacob.
Where is the electric field the strongest?
On the bottom.
Right next to
Wherever you
Wherever you're at.
Right, yeah. It gets weaker the further away we get. That's a key point here. It gets weaker the further away we get. Do you have questions about this? So the forces are acting at a distance, and the shape that field takes is the shape of the electric field or the magnetic field or the gravitational field. Yes?
What happens to the lost forces? Like, say, it's like all those forces are used up. What happens to them?
Yeah, we didn't talk about this when we did our video on charge, but yeah. So there's such a thing as what we call the law of conservation of charge, where this object was neutral, right? And then, well, this is just what it said. This object was neutral, but when I rubbed it on my head, it became negatively charged. So did those negative charges come out of nowhere? No, because what else did it do at the same time? However much negative charge this got, my head must have gotten a positive charge, and that's called the law of conservation of charges. So the more we do this, eventually the charges are going to even out. But it's not because the charges are going away. They're not vanishing. It's just that the negative charges on this are transferring to this to balance out the positive charges on this. So eventually they will balance out. Questions about that? You have other questions about any of this magnetic field and electric field and gravitational field? Remember that those three things form fields. Gravity fields, magnet fields, electric fields. Okay? Okay. Bye.